Having trouble telling how I feel, but I can dance. Couldn't possibly tell you.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we move on to my favorite part, which is biological significance. So you learn all the chemistry behind it, but then ultimately you're like, who cares? Why do we care about enantiomers, diastereomers, and all that? Well, actually, it's extremely important in biology. And the reason for that is because the structure always causes different properties. And so the stereochemistry that we're learning about ultimately leads to biological effects. And so most of nature or biological environments consists of enantiomeric molecules. For example, amino acids, which make peptides and proteins in your body, nucleosides, which make up DNA, carbs that you eat, and phospholipids, which are fats. So as you can see, this chirality or enantiomers are everywhere in biology, and they all display very different properties. So this is a really good diagram to show you that. So for example, let's say that this is a drug and this is an enzyme. And for a drug to work, it has to attach and bind very strongly to that particular enzyme. In this case, these are two enantiomers in that the position of the C, B, and A right here is different, right? If the binding spot of the enzyme requires A, B, and C to be in this particular conformation, where when this goes down it fits perfectly like a lock and key model, then that's going to have really tight binding. But in this case, if C and A have been switched over, now the only binding site is going to be B, right? Where C is not going to bind to the A spot and A is not going to bind to C. So since these two are not going to happen, it's going to cause weak binding. So for just the same exact molecule where something's switched over and thus it shows isomerism, you can have something that tightly binds to an enzyme versus weakly bind to an enzyme. And in order to show you just how important that is, let me very briefly talk about thalidomide. There's a bunch of tongue twisters in this topic. So thalidomide was synthesized in Germany in 1953. And it was a sedative for pregnant women, and it also combated morning sickness. So sounds great, right? But actually it ended up causing thousands of birth defects, so many problems, and it was an absolute disaster. And the reason for that was that they sold this particular drug as a racemic mixture, so that means 1-to-1 ratios of enantiomers. And so this is the drug, the thalidomide, and it has one stereocenter. And we now know that when something has one stereocenter, it has two stereoisomers, right? So we ended up with the S and the R isomers. The S thalidomide was great. It was a sedative to calm nervousness, and it actually worked. But on the other hand, the R isomer caused birth defects. And so the mixture, the 1-to-1 racemic mixture of the two, was absolutely disastrous for pregnant women. And so this is just how crazy and important pharmaceuticals are, and also understanding the fundamental chemistry, because there's so many different occasions where you have two enantiomers that look exactly the same. The only difference is the R or S designation based upon the chiral centers, and you can have something that's either a drug that can help or it's absolutely toxic that causes deaths. And so the reason why these two enantiomers display such different activities is because enantiomers differ in their arrangement of atoms in space, right? And so let me explain this to you in terms of like a biological situation, and we can refer back to this diagram right here. So this means that the S enantiomer of thalidomide can fit into the active site of a specific enzyme. Let's think about it like this enantiomer. It fits perfectly. It's like a key for this specific lock. It works. And so you get the desired effect, which is having a sedative. On the other hand, the R enantiomer can't interact in the same way with that particular site because it has a different 3D structure. And as you can see right here, the C and the A don't match. And as a consequence, it fits a different enzyme active pocket, which triggers different biological effects that ends up being toxic. So basically, the binding pockets of an enzyme and a drug is so important to understand. And so the solution to this problem was to separate the enantiomers from the racemic mixture. So you can have one that is only a sedative and one that's toxic that you just want to get rid of. So now let me show you guys how we can separate enantiomers from a racemic mixture. So how can we actually separate enantiomers from a racemic mixture? So this diagram indicates that you do the chemical synthesis of thalidomide from achiral starting materials and you get this racemic 1-to-1 mixture of the S and R isomers. So now we have to separate these into their specific enantiomers. So how can we do this? Well, the first option is using their physical properties. So physical properties such as boiling point, solubility, etc. This can help you to separate two things apart. Another possibility is using chemical properties. And in this case, it's if one stereoisomer maybe reacts faster or slower than the other, and you can use its kinetics to separate them. But basically, what people came up with in order to separate the enantiomers is to use diastereomers. And the reason for that is because diastereomers have different physical properties, while enantiomers have no difference in physical property except the direction of plane polarized light. So remember, enantiomers can turn plane polarized light in opposite directions, but that's not a very useful physical property when you want to separate two things apart. Diastereomers, on the other hand, have very different physical properties that allow for this separation to occur. So now let's look at this. This diagram right here is the resolution strategy, where enantiomers are not easily separated because they have the same properties, but diastereomers are. So we start out with these two enantiomers, but then we add a chiral reagent, one or more stereocenters. And then we create these diastereomers, which now have different properties. For example, they have different boiling points, and you can separate them by distillation. And so step one was converting enantiomers into diastereomers, in this case by adding a chiral reagent. And then the second step was to separate the diastereomers based upon their physical properties. And then all you have to do is reverse the diastereomer formation to give the separated enantiomers. And in this case, all you have to do is cleave off the chiral reagent. So this is an organic synthesis problem, but someone figured out that you can go from enantiomers to diastereomers and back to separated enantiomers, which allows us to separate enantiomers from racemic mixtures and use them for really important biomedical applications.